Okay, in this section on measured numbers, we're going to look at the error, accuracy, and precision. So what are we talking about when we're looking at these measures? The difference between the true or best accepted value of some quantity and the measured value is the error. So if you measure some value and you've got a reference somewhere that tells you what the value should be, and you take an error calculation between the two, you're going to come up with a value that says you're 10% off or less than 10% off or less than 1% off, and that's going to give you your error between an established value. A measurement is said to be accurate then if the error is small. Accuracy is an indication then of the range of error in a measurement. For example, if you measure the thickness of a 10 millimeter gauge block with a micrometer and find that it is 10.8 millimeters, the reading is not accurate because the gauge block is considered to be the working standard. If you measure 10.02 to within a hundredth, 200th of a millimeter, the reading is accurate because it is a reasonable agreement with the standard. So you have to determine, what the standard measure of error is. Plus or minus 1%, plus or minus 10%, plus or minus 200th of a millimeter. You just have to determine that, and we're going to see some of that when we look at measuring things like resistors, and we're going to look at how they are coded so that you can determine what the accuracy in fact is. Another term associated with the quality of measurement then is precision. Precision is a measure of the repeatability or consistency of a measurement of some quantity. It is possible to have a precise measurement in which a series of readings are not scattered, but each measurement is inaccurate because of an instrument error. For example, a meter may be out of calibration and produce inaccurate but consistent, precise results. However, it is not possible to have an accurate instrument unless it's also precise. Significant digits then become important. The digits in a measured number that are known to be correct are called the significant digits. Most measuring instruments show the proper number of significant digits, but some instruments can show digits that are not significant, leaving it to the user to determine what should be reported. This may occur because of the effect of something called loading. A meter can change the actual reading in a circuit by its very presence. It's important to recognize when a reading may be inaccurate. You should not report digits that are known to be inaccurate. Another area that as students and in this class that we run into quite often is you do a calculation, you don't account for the significant digits, and you load the numbers into your calculator, the values into the calculator, and you do a calculation, and you come up with some wildly crazy number that cannot be correct because the data is only as good as the information you put in. So if you end up with some wildly crazy number and say, well, that's what the calculator value gave me, that's immediately wrong. You need to be thinking about that all the time because it is immediately suspect. Another problem with significant digits occurs when you perform mathematical operations with numbers. The number of significant digits should never exceed the number in the original measurement. For example, if 1 volt is divided by 3 ohms, a calculator will show 0.333333, and it can go on infinitum. Since the original numbers each contain 2 significant digits, the answer can only be reported as 0.33, so it can only be 33 hundredths of an amp, the same number of significant digits. The rules for determining if a reported digit is significant are: 1, non-zero digits are always considered to be significant. 2, zeros to the left of the first non-zero digit are never significant. 3, zeros between non-zero digits are always significant. 4, Zeros to the right of the decimal point for a decimal number are significant. And 5, zeros to the left of the decimal point with a whole number may or may not be significant depending on the measurement. For example, the number 12,100 ohms can have 3, 4, or 5 significant digits. To clarify, the significant digits, scientific notation, or metric prefix should be used. So for example, 12.10 k ohms has 4 significant digits. So looking at an example, express the measured number 4,300 with 2, 3, and 4 significant digits. Zeros to the right of the decimal point in a decimal number are significant. Therefore, to show 2 significant digits, we write 4.3 times 10 to the third. So you can see we're making the number significant by using the exponentials to give us our accuracy. To show 3 significant digits, we write 4.30 times 10 to the third. And to show 4 significant digits, we then write 4.300 times 10 to the third. In this example, they want us to underline the significant digits in each of the following measurements. So you're just going to do this by inspection. So 40.1 has 3 significant digits according to Rule 4. 0.3040 has 4 significant digits according to Rules 2 and 3. 1.20 times 10 to the fifth has 3 significant digits according to Rule 4. 120,000, though, has at least 2 significant digits, although the number has the same value as in C above. Zeros in this example are uncertain. See Rule 5. This is not a recommended method for reporting a measured quantity. Use scientific notation or a metric prefix in this case. And they ask you to look at the previous example. 0.00502 has 3 significant digits according to Rules 2 and 3. So you need to become familiar with those rules. What I would do is I would keep those rules handy in a notebook so that you can refer to them throughout the course when you're trying to determine how are you going to handle significant digits for any given problem and situation. We'll stop there and come back to measured numbers for round off.